Okay, so where we're going to start off today is continuing in chapter 5. We have already started this chapter, and the introductory part of this chapter, we talked about heat energy, what heat is, what heat is not. We focused in on defining endo versus exothermic reactions, and we're going to talk about that a little bit more today. But I want to start off with some vocabulary. This is a new word for us, enthalpy. It's just a fancy word that means heat energy. Its variable is a capitalized H. H stands for heat. And we're not going to see just the letter H as much as we are going to see delta H. Okay, delta of course means change. We're going to see the change in enthalpy. How does the heat energy change in particular reactions? And we looked at this a little bit at the beginning of the chapter, and I drew for you what are called energy curves. Okay, some that look like this, for example, and we put numbers up on the y-axis, and we did a subtraction. Heat of the products minus heat of the reactants, and depending on whether that number gave us a negative or a positive answer, told us whether something was endo or exothermic. And we're going to look at that again today. All right, so a characteristic of enthalpy is that it is an extensive property. Okay, we use the word intensive probably a little bit more. You talk about it in Chem 1 about how density is the ultimate example of an intensive property, a property that remains constant no matter how much of something you have. I think we use the example of an ice cube versus an iceberg. Ice cube, iceberg, both have the same density, for example, the same melting point. Those are intensive properties. Extensive, of course, would then mean some kind of property that does change depending on how much of something you have. Enthalpy is an example. Okay, another example would be mass, volume, weight. Right? These are all properties that change depending on how much of some material you have. And I'll give you a real life situation. Imagine you have a lit candle in front of you, and if you hold your hand above the flame of a lit candle, and I don't mean like right above the flame, like in the flame, but just above the flame, you're going to feel a little bit of heat, right? Okay. Whereas imagine you are standing next to a bonfire. Okay. You'd be feeling much more heat, correct? Yes. Okay. As the amount of reacting material gets much, much greater, candle, bonfire, the amount of heat also, the amount of heat released is also much greater. Okay? Enthalpy, heat, is an extensive property. This is what a question addressing this issue is going to look like. You're typically going to see these more in multiple choice. Okay, you've been given a reaction here. It's already balanced. And we're given a delta H value right here. Okay, it's positive. That tells me it's endothermic. And if you'll notice, if you move your eyes from this line down to this line, what's happened here? Okay, what's happened from one line to the other? Yeah. Okay, so the coefficients have just been doubled, multiplied by 2, correct? Yeah. Well, look what happens to the enthalpy change as well. It's also been multiplied by 2. When we double the amount of reacting material, the enthalpy change is also doubled. Okay, because remember, coefficients are really just giving you relative amounts of moles. So if you double the amount of moles, then we're going to double this enthalpy change. And in multiple choice, what you'll usually see is, you're given this reaction, you're given this heat change, you're given the new reaction, and then it'll say, what is the enthalpy change for this second reaction? Okay? Whatever you do to the coefficients, you're also going to do to delta H. So here's another vocabulary word for us, calorimetry. The science of measuring heat. And when you're measuring heat, we're going to use a piece of equipment called a calorimeter. And there's 2 types. One is called a coffee cup calorimeter, and I did not come up with that name, that's actually what it's called. Another is called a bomb calorimeter. Please don't ask me why they call it a bomb calorimeter. There is no bomb going off here. Okay? But one is more complex than the other. Okay? You've got, in this simpler one, they'll use styrofoam cups. Now, what's so special about styrofoam? I mean, why do we use styrofoam when we're drinking hot coffee or hot tea or whatever? Yeah, thank you for using that word. Styrofoam is an excellent insulator. It does not allow much transfer of heat. Cardboard is another pretty good insulator. That's why, Starbucks uses cardboard for all of its cups. So this is a material that's good as pretty good as an insulator. So we're going to use this to help us measure changes in heat. This one, okay, slightly more complex design. We've got an exterior chamber, we have an interior chamber. Inside this interior chamber, you would have some sort of chemical reaction going on. The space between the 2 chambers is filled with constantly flowing water. Okay? And although we would not use a bomb calorimeter to talk about nuclear reactions, this setup is very similar to how a cooling tower in within a nuclear power plant works. And you may not have seen one in person, but I'm sure you've seen a picture of these huge concrete structures. They're buildings that kind of look like this. It's not even really a building. Okay? It's just this big concrete structure, and somewhere inside you've got this interior chamber where it's not that there's a chemical reaction going on, there is a nuclear reaction going on. And nuclear reactions that go on in nuclear power plants are very, 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 very exothermic. Okay, now what do I mean by that? Yeah, it's like really, really hot, wicked, wicked hot. Okay, and so these cooling towers, much like this design as well, will have water constantly flowing around that interior chamber you'll notice nuclear power plants are almost always situated next to some sort of flowing body of water. And these nuclear power plants will pull water from that source and run it around that chamber to keep the temperature under control. And when nuclear power plants have what's called a nuclear meltdown, usually what has happened is something has happened with that water supply. Either the water source has been cut off, or something with the flowing mechanism has shut down. And think about it. If the water stops flowing and is just sitting there around that interior chamber that has a reaction that is really, really hot, releasing a ton of heat, what's going to happen to the temperature of the water? Yeah, it's going to go up, like maybe dramatically going to go up. Maybe it goes up so high that the water starts to boil, and then maybe that interior chamber starts to melt, and then you have nuclear waste, leaching into the groundwater, and we have animals with 3 eyes, and it's terrible. Okay? Now, again, we're not talking about nuclear chemistry here, but this setup of a bomb calorimeter is very similar in the design of a cooling tower. But I want you to notice, though, in both pictures, we have thermometers. In both kinds of calorimeters, some sort of reaction is going on, and we are monitoring the temperature. And whatever the temperature is doing is giving us information about that reaction. Okay, so before we get to the math, I just want to review a few terms with you. Okay, and we're going to start here in the middle. Okay, specific heat capacity, which is abbreviated with a lowercase c. All right, these are its units. Joules, that's just a unit of energy. Joules per degree Celsius gram, or Kelvin gram. Let me define it for you first. Specific heat capacity is an amount of heat required to raise the temperature of some substance by 1 degree Celsius, or Kelvin. It's the amount of energy required to raise the temperature of some substance by 1 degree Celsius, or Kelvin. And let me just give you kind of a hypothetical situation, okay, because you may see some multiple choice questions about this. Let's imagine that you have 2 buckets of exactly equal size. And one bucket is filled with water, and the other bucket is filled with iron filings, so pure iron. And you're going to apply some heat to both buckets. You're going to apply the same amount of heat. All right? Well, I'm going to tell you that the temperature of the iron is going to rise higher. Okay? Let me say that again. Let me let that sink in a little bit. I'm going to apply the same amount of heat to both buckets. But I'm telling you, because metals are such good conductors, when we monitor how hot does the iron get, how hot does the water get, the iron is going to rise to a much higher temperature than the water. So let me ask you this. Let's pretend this is a multiple choice question. Which substance, the iron or the water, which one will have the lower specific heat capacity? Correct. The iron will have the lower specific heat capacity. Let me say that to you in another way. It's like it's easier to heat up the iron, okay, because iron is such a good conductor. Okay, so it's an amount of heat. How much heat does it take to change the temperature of this substance? In this scenario, the iron will change its temperature much more easily than the water. Now, mathematically, where would you use this? In this equation, which, by the way, is the very first equation in this thermochemistry section of your equation sheet. It's there for you. All the variables are defined. Okay, Q is heat, usually going to be in joules, maybe kilojoules sometimes, but usually joules. M is mass in grams. C is specific heat capacity. Delta T, change in temperature. Okay. I call this the MCAT equation. And if you will now move your eyes from here up to the top, what's the difference? What's missing? Yeah. Okay. There's no grams up here. Right? There's no unit of mass. This is just heat capacity, not specific heat capacity, just heat capacity. It's abbreviated with a capital C. And since there is no unit of mass, I'm not going to plug this into this equation because this equation has mass in it. You would use just plain old heat capacity in a setting like this. Capital C, no mass. Okay, this is not on your equation sheet, but this is something that could be very, very helpful. Okay, we're going to do a problem where we're going to use that equation, as a matter of fact. And if you look down to the bottom here, this one looks kind of similar to this. The only difference is instead of a unit of mass, it's a unit of moles. Molar heat capacity you could use in a very similar situation to this, except instead of a mass, you would plug in a number of moles. All three of these, you know, when do we use them? It depends on what's given to you. You know, it just sort of depends on what the situation is presenting you with. It is worth noting that all things on this slide, all three of these concepts, these are intensive properties. Okay.
Students, if you are participating in today's award ceremony, you should start to make your way to the auditorium at this time. Teachers, you received a list again this morning with the students who are participating. Again, if you are participating in today's award ceremony, please start making your way to the auditorium. Thank you.
All three of these things on this slide are intensive properties. They do not change no matter how much of the material you have. An ice cube and an iceberg have the same specific heat capacity. It's plain old heat enthalpy. That's what's extensive. Okay? Okay. Now, we're going to do some calorimetry problems in just a second, but before we do, I want to sort of set the scene for you on the general setup of pretty much any calorimetry problem. Calorimetry problems are going to have two parts to them, okay? Whatever the word problem describes, there's always something releasing heat and something absorbing the heat. Okay? And I'm going to give you a hypothetical situation. Let's say I have in my possession a lead pipe. I don't know why I would have a lead pipe, but let's just say I do. And I take that lead pipe and I put it in the Bunsen burner and I heat it up so it's nice and hot. I then take that very, very hot metal and I put it into a beaker of room temperature water. Yeah, exactly. Okay. Those are my two pieces. One piece is the lead pipe. The other part of this scenario is the room temperature water. And let's think about each piece individually. What is going to happen once I put the lead pipe into the water? What's going to happen to the temperature of that pipe? Correct. It's going to fall. It's going to cool down. So what's going to happen to the temperature of the room temperature water? What's going to happen with that? Correct. Okay, it's going to heat up. And the pipe is going to cool down, the water's going to heat up, and those two processes are going to keep happening until they reach the same temperature. Tell me, you just said, correctly by the way, that the the lead pipe would be cooling down. Does that sound to you like the pipe is releasing heat or absorbing? Right, the lead pipe is releasing heat, which means what about the water in the beaker? Yeah, it must be gaining it. So here again is those two parts to this calorimetry situation. The energy released by the lead pipe will all be absorbed by the water. And there's that equation down at the bottom. I call it the MCAT equation. It's there. We're going to use it a lot. Okay, and what I would do if this were a math problem is I would have one set of calculations for the lead pipe and another set of calculations for the water. Okay, now, delta T. Delta T, that's change in temperature, right? Okay, well, I'm going to calculate that as final temperature minus initial. Okay, now I want you to think about the lead pipe. You said it's cooling down, so make up some temperatures if you want. Make up some temperatures to put into this situation right here. For the lead pipe, if I plug in numbers here and I multiply these all together, what kind of a result am I going to get? Yeah. Negative. Okay. Well, guys, what does a negative heat value mean? Yeah, exothermic, exactly. And doesn't that mean, isn't exothermic when energy is released or lost? Okay, so the math is now starting to support the concept. Okay, let's think about the water. Make up some numbers if you want. You said the water would be heating up. If I plug in numbers here and multiply, I'm going to get, right, positive. How do you make something negative equal something positive? Correct. Okay. I'm going to put a negative sign there. It does not matter which side you put it on. Okay, so here's the take-home message. In any kind of calorimetry situation, you'll have two parts. One thing is releasing heat, one thing is absorbing. Their energies are equal but opposite in sign. Because one thing will be losing heat, exo. One thing will be gaining, endo. Equal but opposite in sign. Okay. So I want you to try these problems, and I think you'll be able to get through them pretty easily on your own. The only bit of caution I want to say to you is be careful with your units in number 1. Try these. Okay. Check your answer. And there's 3 things that I want to say about this problem. Number 1, I got a lot of people asking, did you have to put the mass into grams? And the answer is yes, you do, because if you looked at the units for the specific heat capacity right here, you saw units of joules per gram degrees Celsius. So yes, this had to be in grams. The second thing I want to say, think about the units I just said, joules per gram degree Celsius. So why is it okay for me to have put Kelvin in there? Guys, realize the difference between two Kelvin temperatures and the difference between those same temperatures in Celsius, the difference is the same. So actually, this is okay. It doesn't matter. The third thing, does your answer have to be in kilojoules? No, it doesn't. You could just, you need 2 significant figures. You could have left your answer in joules. Maybe you did it in scientific notation, 2.9 times 10 to the 6 joules. That's fine. I just think kilojoules is a little neater, a little tidier, but that's just me. Okay? In number 2, some of you noticed that there's a piece of information missing in this problem, and it's the specific heat capacity of water. And ladies and gentlemen, I hate to tell you this, you have to just commit it to memory. It is not on your equation sheet. Specific heat capacity for water. 4.184 joules per gram degrees Celsius. Learn it, know it. Do number 2. Okay, there's number 2. Check your answer. And let me just say something about, problems like this. Whenever I do my delta T here, I always do final minus initial. Okay, I always stick to that rule. However, I want you to be aware that your textbook and a lot of these online resources that you might come across, they do delta T a little differently. They take the absolute value of delta T. Okay, so no matter what, they always take the absolute value, which means the delta T is always positive. And if you do that, you can forget about this negative sign here. You don't have to say the energies are equal but opposite in sign. And I know what you're thinking. That sounds a lot easier. Why didn't she just teach it to us that way in the first place? Well, I personally think that doing final minus initial and seeing whether your heat is negative or positive is something valuable for you to know. It shows you which part of this scenario is exothermic, which part is endothermic, which part is losing heat, which part is gaining heat. Do you have to do final minus initial? No. You can do your textbook's method, but I'm always going to do it this way. I like this way. To me, it gives me a richer understanding, but that's up to you. Okay. Now, let me tell you something. Problem number 1 was Chem 1 level. This one is like Chem 1 honors. You can see where I'm going with this. Here's one that's a little bit more your speed. Okay, and this word challenge, it's not even really a challenge problem. It's really not that difficult of a problem. Okay, but let's look at it. All right, it says we've got a 1.8 gram sample of phenol. It's being burned in a bomb calorimeter. Well, I'm going to stop there and I'm going to draw a picture because I'm a very visual person. So a bomb calorimeter, guys, has an outer chamber, an interior chamber. We've got water in between those two chambers. This reaction, this phenol reaction, is happening inside that interior chamber. Okay? They give us some information about the bomb calorimeter. They give us a heat capacity. The temperature of the calorimeter plus its contents increased from this to that. Okay? Now, I get a lot of questions about what does that word contents include? I mean, is that everything? And no, it isn't. It's not everything. Okay, and this is going to seem a little weird. The calorimeter and its contents includes the outer box, the water, the interior box, but not the reaction that's going on inside it. Okay? At the beginning of this chapter, we talked a lot about the difference between the system versus the surroundings. In this example, the phenol, that reaction, is the system, and everything around it is the surroundings. Okay, so this temperature increase is of the surroundings. And, you know, if it makes you more comfortable, just think of the water. Okay? And let's think about this for a second. If the water is heating up, it's getting warmer, what does that mean about this reaction? Is this reaction releasing heat or absorbing heat? Yeah, it's releasing. I'm gonna draw some arrows. Okay, this reaction, the system, is releasing heat out into the water, okay, out into those surroundings. What is the heat of combustion per gram of phenol per mole of phenol? Okay, well, just like all of our other calorimetry problems, we've got two parts to this. One part is our system, the other is the surroundings. Okay, well, our system is that phenol reaction. The heat released by the phenol reaction will be equal but opposite in sign to the heat gained by the surroundings, I'm going to say by the calorimeter. Okay? So the heat released by the phenol reaction is equal but opposite in sign to the heat gained by the calorimeter. Okay, well, what is the heat of combustion? That's the reaction part. That's the phenol reaction. There's my unknown. I'm going to circle it. If this is my unknown, that means I must have numbers to put in all over here. So let's look at what information we've been given. We've got two temperatures. Okay, that's going to allow me to calculate a delta T. And then I've also got this piece of information. And I want you to pay attention to the units here. All right? The units for Q are joules or kilojoules, right? Okay. Look at these units. kilojoules per degree Celsius. How do I take something that's in kilojoules per degree Celsius and get rid of that per degree Celsius? What do you do? What do you do? Multiply times what? Yeah, times degree Celsius. To be more specific, you're going to multiply by this. If you look back in your notes, guys, we wrote down an equation that looks like that. And that's exactly what we're going to do here. Okay? So let me get to a new page here. And so let's calculate something for this calorimeter. I'm going to do final minus initial. Okay, so that's a positive number. That is the amount of heat absorbed by the calorimeter. Well, let's go back to what we said. The heat of the phenol reaction would be equal but opposite in sign to the heat gained by the calorimeter, which I now have a number to plug in there. Okay. And guys, the fact that this is negative, this should make sense. We said that this phenol reaction was releasing heat out into the calorimeter, releasing heat, exothermic. Okay? Exothermic heats are negative. It should be negative. Okay, but that's not quite what they asked us for. They asked us for the heat of this reaction per gram of phenol. Well, guys, per mathematically just means divided by. And the problem gave us the mass of the phenol. All I have to do is divide it out. The last part this problem asks is, what is the heat of the combustion per mole of phenol? And that's easy, okay? I have the mass. I was given the formula for phenol. All I have to do is use my periodic table to calculate how many moles that is. And now I just divide. So guys, the take-home message here is, these calorimetry problems, you have two parts. Something's releasing heat, something's absorbing heat, equal but opposite in sign. The tricky part, honestly, is just how do you solve for the heat of one side? Sometimes you use MCAT. Sometimes you do something like this. Next class, we're going to see even another way to calculate a heat. I know you're excited. I'm excited too. Okay? So I'm going to stop there.